Let me first introduce myself. I'm Chen Zhao, and I'm a PhD student from Chinese Academy of Science. And it's nice to see you again. And last time I talked about the Julia ZX calculus package. And today I'm going to talk about my recent work analyzing the barren plateau phenomenon in quantum neural network training with the ZX calculus. So in NISQ era, we will consider variational quantum algorithms. And these algorithms are widely used in, for example, the quantum chemistry, the VQE, and combinatorial optimization, the QAOA algorithm, and some quantum machine learning algorithms. And in all of these algorithms, we will train parameterized quantum circuits, and it's also called quantum neural network. And in this algorithm, there will be a part for quantum processor, and we will apply a parameterized quantum circuit U theta to an initial state psi 0 and measure it. We will compute a cost function L theta according to the measurement result, and we will use the classical processors to update these parameters. And again, after some iteration, the cost function may converge. And there will be a lot of methods to train this parameterized quantum circuit. For example, we will use gradient-based training methods. For example, the parameter shifting, and there are some gradient-free methods. When we use the gradient-based method, we should estimate the gradient. So the barren plateau phenomenon is that it tells us the gradient will vanish exponentially as the system size grows up. That means if the system size is large, the gradient is hard to estimate. And then the parameterized quantum circuit will be very hard to train. So let me just take a brief, I will introduce briefly about the barren plateaus phenomenon. So let's consider the ansatz. Let's consider the parameterized quantum circuit U theta and Hamiltonian and initialized state, initial state. Then the expectation of the Hamiltonian can be represented as this by the definition, and the partial derivative will be like this by the chain rule. Then if we regard the V and the W as random unitaries, then the gradient, the partial derivative, can be regarded as random variables. So what would the expectation and variance be? For random unitaries, there are a distribution called Haar distribution, which can be regarded as a uniform random unitary. And T-design is a notion that characterizes how a set of unitary be close to Haar random unitary. When a set of unitaries is said to be T-design, then we cannot differ it from the Haar random unitary up to the T moment. So if we use the assumption of T design, for example, if if V and W are one design, then the expectation of the gradient will be 0. And if W and V are two design, then the variance can be computed symbolically. Then the variance is exponential small. And this is the first result about the barren plateau. And later, there are some results said if the parameterized quantum circuits are locally to design, then there also exists a barren plateaus phenomenon for even shallow circuits. But these results are under the assumption of T design. But if we analyze some concrete parameterized circuits, this assumption may be failed. Then we cannot use this theorem. So how can we analyze some concrete parameterized circuit? We can use the ZX calculus. So I believe that everyone here is very familiar with the ZX calculus. So in ZX calculus, we will deal with ZX diagrams, and ZX diagram can be regarded as tensor networks generated with the Z spider and X spiders. And ZX diagram can represent quantum states and quantum gates. And we also can use the rewriting rules to rewrite ZX diagrams. And we will focus on a canonical form of ZX diagram, the graph-like ZX diagram, where the all spiders are Z spiders, and Z spider can only connect it with Hadamard edges. And parallel Hadamard edges can be removed, and also self loops can be removed. And to compute the variance and the expectation of some value, we have to consider the scalar, because the previous rules will ignore the scalar, and we will give the rewriting rules with the scalar. The scalar is very important here. So let's first take some make some assumptions that we only consider the parameterized quantum circuit which generated with the C0 gate, rotation Z, and Hadamard gate, because these gates are universal, and we assume that all the parameters are independent, and each parameter is a uniform random variable in the interval 0 to 2 pi. Then computing the expectation and variance of the gradient will become the integration. So the routine is that we will first convert the parameterized quantum circuit to parameterized graph-like ZX diagram, and we will integrate the ZX diagram over parameters. So first, we will represent the expectation of Hamiltonian as ZX diagram. If we consider a parameterized quantum circuit U theta, then use the converting rule, we can convert it to a graph-like ZX diagram up to a constant. Then by definition, the expectation of the Hamiltonian can be represented as this ZX diagram. So the expectation can be represented as a ZX diagram. Let's consider now the derivative. If we expand the two spider corresponding to theta j as the by the definition of this spider, and we take the partial derivative, then we can get this kind of spider. So if we want to take the derivative of theta j, we just add half of pi, then connect them with the x spider with phase pi. So the partial derivative of the expectation value of the Hamiltonian is also a ZX diagram. If we want to compute the expectation of the gradient, we have to integrate the ZX diagram. So, and we can use the integration rule. We prove this integration rule. If we want to integrate over the parameter alpha, we just set the alpha to 0 and connect them with a normal edge. So the integration is again a ZX diagram. So let's consider the integration over theta j. Because we take the partial derivative on theta j, then there will be a x spider with phase pi. Then we take the integration over theta j. We can connect them with a normal edge and set the phase to 0. Then by the rewriting rule, we will have two parallel Hadamard edges. And by the Hopf rule, we can remove these Hadamard edges. Then we will get a individual Z spider. And this spider with phase pi is just 0. And by now we can prove that the expectation of gradient is 0. And it is much more simpler than the previous result. Now let's consider the variance of the gradient. The variance, first we have to represent the variance as the X diagram. The variance is just integration over the parameters of this square. And this square is just this ZX diagram. And in this ZX diagram, each parameter corresponds to two of these spiders. And when we integrate one of these parameter, for example, we will integrate over alpha, then we can get the result as a sum of 3 ZX diagrams. And it will be much more complicated to compute the variance because when we have a lot of parameters, there will be a lot of terms. And we denote the T1, T2, T3 be these 3 ZX diagrams. And now we introduced a new notation, VA1 to AM, to represent the following ZX diagram, where AJ is in T1, T2, T3. And VA1 to AM means that we connect AJ, we connect the spiders corresponding to theta j with AJ. Because here, after integration, there will be 3 terms, the T1, T2, T3. And here we just record them. Then we will have this theorem. The variation of the gradient can be represented as this kind of sum. And it's a sum over 3 to the n minus 1 terms. It is exponential. But in many cases, we can simplify these terms, that we don't need to compute these terms individually, and we have many of techniques. For example, if we consider two of parameters, theta j and theta k. If theta j and theta k are connected with a Hadamard edge, then after integration, this Hadamard edge can be removed up to coefficient m AJAK, and M AJAK can be regarded as a 3x3 matrix. And if in a graph like ZX diagram, if there are many of these Hadamard edges connecting two parameterized spiders, then these edges can be removed by this relation. So let's consider an extreme case that in this graph like ZX diagram, all spiders are parameterized. Then these Hadamard edges can all of these Hadamard edges can be removed after integration. Then after integration, this ZX diagram will break into many small parts, and each of small parts is just this scalar. And this scalar are connected with the matrix M. Then the variation of the gradient can be represented as this tensor network. Here the black circle are the copy tensor, and the white circle are the matrix M. And the projection identify the parameter of the partial derivative we take. So computing the variance is equivalent to contracting this kind of tensor network. So let's see some examples. Let's consider the hardware efficient ansatz of the following form. We first convert it to graph like ZX diagram. It will like this. Then we can use in this ZX diagram, the spider with this are parameterized, and this is a spider of phase 0. And we can use this relation on these edges. And for this part, we can use similar techniques to remove it. Then the variance can be represented as this tensor network. So if we want to analyze the barren plateaus phenomenon, we just contract this tensor network. And the building block of this tensor network is EM, which is defined as this. And it is a 9x9 matrix, and the maximum eigenvalue is 1. And the dimension of the eigenspace corresponding to the eigenvalue 1 is 2. And for each layer, it consists of many of this EM. And for a layer, LT, the LT is a matrix of dimension 3 to the m times 3 to the m. Then the maximal eigenvalue of LT is also 1, and the eigenspace of LT corresponding to the eigenvalue 1 is generated with these two vector. Then the variance of gradient will converge to this value exponentially as L1, L2 grows up. This value is an exponential small value in n. N is the qubit number. So there is this barren plateaus phenomenon in hardware efficient ansatz that the variance of the gradient vanishes exponentially as the qubit number and the layer number grow up. Also, we consider the MPS-inspired ansatz, and with the respect to this Hamiltonian, there exists BP phenomenon in MPS-inspired ansatz that the variance of the gradient will vanish exponentially as the qubit number grow up. And there are some results about there are some ansatz that is trainable. That we can prove that in the QCNN ansatz and the tree tensor network ansatz, there is no barren plateau phenomenon, and these two kind of ansatz are trainable. So in conclusion, we propose a general method to analyze the barren plateaus phenomenon for a large class of parameterized quantum circuits with the ZX calculus. And we consider the differentiation and integration for ZX diagrams. And we use these techniques to analyze the BP phenomenon for concrete ansatz. But there are still a lot of things to do. First is that we need to develop some software for these techniques that we can analyze some concrete parameterized circuits automatically. And we have to analyze other ansatz and find more trainable ansatz. And it is still unknown that whether these techniques can be used to analyze the initialization strategy and the correlation of parameters. And can we find other application for these techniques? For example, for other problems where the integration over random unitaries are needed. And is there any general theory for the differentiation and integration in the ZX calculus or other graphical calculus? So that's all my talk. Thank you.
Thanks, the speaker.